Okay, so let us say you open a product page. Behind the scenes, your request goes to a server, and the server has to do real work. Read a couple of database rows, calculate the price, pull in the ratings, check the stock, and all of that. Let's say that takes about 200 milliseconds. Fine. Now you refresh the exact same page, and this time it comes back almost instantly, like 3 milliseconds. Same page, same server, but almost 70 times faster. So, what happened in between? What happened is, the first time someone kept a copy of the answer, so the second request never did all that work again. It just grabbed the copy, and that, at high level, is caching. A cache is simply a copy of an expensive answer kept somewhere fast, so the next request can reuse it instead of redoing the work. And honestly, that part is easy. Storing a copy is easy. Here is the hard part. Back in the database, let's say the seller changes the price. 599 becomes 549. The database now says 549, but the cache, it is still holding 599. So it is fast and it is wrong. And that is the whole tension of this topic, right? The database has the truth. The cache only has a copy. So adding a cache is easy. Knowing when that copy is still okay to use, that is the actual job. Let's build it up properly. So, first thing, and this is where people get confused. A cache does not make everything fast. It only makes the hits fast. And quick note upfront, we are mostly talking about the reads here. The same thing asked for again and again. Changing the data writing is the harder case, and we'll get to that. Let me show you. Let's say 10 people ask for the same product page in a minute. The first one is a miss. The copy is not there yet. So we do the full 200 milliseconds of the work and we store the answer. But the next 9 are hits. They just get the copy, about 3 milliseconds each. So instead of 10 times 200, that is 2000 milliseconds of work, we did one miss plus 9 cheap hits, about 227. That is almost 90% less work. And the database went from 10 reads down to 1. That is the easy win. But here is the thing. Notice it was the hits that were cheap. A miss still pays full price. So a cache is not really a speed button. It is a bet on your hit rate. That is just a fraction of requests you can answer from the copy. And it is a simple blend of the two. Our hit is about 3 milliseconds and a miss is the full 200. So at a 50% hit rate, your average is only about halfway down around 100 milliseconds. But push the hit rate up to 99% and it drops to about 5. Same cache, the hit rate is the whole story. And those last few points matter the most. One caution as well, tying back to the latency video. If you are missing even a few percent of the time, the people who miss still wait for the full 200. So your slow tail, the P95, P99, that is the miss path, not the average. And honestly, the bigger win is not even the speed, it is offload. Think about it. Let's say you are serving 10,000 requests a second and each one hits the database 4 times. That is 40,000 queries a second landing on your database. Now, put a cache in front at an 85% hit rate. Only 15% get through. And suddenly, the database is seeing about 6,000 a second instead of 40,000. Even if users were already happy with the speed, that is the difference between a database that copes and one that falls over. So, a cache is a scaling tool first and a speed tool second. That is the important part. Okay, second surprise. It is not one cache. A single request can pass several copies on its way to the answer. Let's actually walk it. You ask for a page. First stop, your own browser cache, right there on your laptop. That is private, just for you. You met that one back in the HTTP video. If it is not there, next stop, the CDN, that shared cache near you from the last video. Still not there, the request finally reaches your app server. And now the new one. The app server does not go straight to the database. It first checks an application cache, usually something like Redis or Memcached, which is just a fast in memory store sitting in front of the database shared by all your servers. And only if that misses does it finally hit the database, the source of truth. And here is the thing, at every one of these stops, it is the exact same two questions. Do I have this? And can I trust my copy? One pattern, a few different places. Now, that app cache in front of the database, that is the one we have not seen yet. And here is the cache hiding inside it. So let's build it up properly first. The common pattern is called cache aside. And at high level, it is just your code managing the cache by hand. The read path is exactly what you would guess. A request comes in for product 42. Step 1. Ask the cache, do you have product 42? If yes, that's a hit. Return it. Done. If no, a miss. Then go read the database. Store that answer in the cache with a little timer on it and return it. So the next person gets the copy. Simple enough. But notice one thing, and it matters a lot in second. The cache does not magically know when the database changes. Our code has to keep them in sync. One quick thing, because it is a common mix-up, the database itself keeps hot data in memory as well. But you do not have to worry about that one because the database manages it itself, keeping that inside copy in step with its own data. Your app cache is the opposite. It sits outside the database and nobody keeps it honest but your own code. And that is exactly why the next problem even exists. Okay, so the whole hard half of the caching is really one question. When is my copy still okay to use? Because again, the database has the truth and the cache only has a copy. Go back to our price. The seller changes it to 549. The database updates, but the cache is still sitting there holding 599, happily serving it to everyone. Fast and wrong. And this is genuinely one of the hardest problems in all of the computing. There is a famous joke that two hardest things in the computer science are cache invalidation and naming things. And honestly, this whole section is the first one. So, how do we decide if a copy is still good? The simplest way is just a timer, a TTL, a time to live. When we store a copy, we give it a lifespan. Let's say keep this one for 60 seconds. You saw the HTTP flavor of this in the CDN video, a cache control header. But in our app cache, the TTL is just a number we set on the key when we save it. Inside that window, the copy is fresh. Just use it. After it, the copy is stale. Go recheck. But here is the part people get wrong, so hold on to it. A TTL does not mean the data changes every 60 seconds. The price might not change for a week. The timer just means after 60 seconds, do not reuse this copy without checking. It is a promise to recheck, not a claim that anything actually changed. That is the whole idea of freshness. Right. So the cache does not know the database changed. Our code has to handle it. So when we write, when that price actually changes, what do we do? The rule is short. Update the database first, then delete the cache key. Not update the cache, delete it. You write 549 to the database, then you just throw away the old cached copy. And the next person who asks gets a miss, reads the fresh 549 from the database and caches that. Clean. Now, the interesting bit is why that exact order matters. Because doing it the other way, delete first, then update the database, honestly looks completely fine, right? So, before I show you, have a quick guess at what could possibly go wrong there. Okay, let's walk it slowly. Step 1, the writer deletes the cached copy. So far, so good. But right in the tiny gap before the database write lands, a reader shows up. Step 2, the reader misses because the cache is now empty. So it goes to the database and the database still says 599. Remember, our write has not actually happened yet. Step 3, the reader does the perfectly normal thing and stores that 599 back into the cache. And now, step 4, the writer finally finishes and the database becomes 549. And look where we ended up. The database says 549, the cache says 599. And it will stay wrong until the timer runs out. One reader in one tiny window refill the old value. That is the classic caching bug. Now flip the order, database first, then delete. And that window basically closes. The next reader just pulls the fresh value. And one more small thing, we delete the key. We do not try to write the new value to it. Because a delete is simple and safe. Just fetch it fresh next time. So, for cache aside, the pattern we are using, update the database, then delete the key. There are deeper setups that write through the cache instead, but for us, delete is the safe default. Okay, last piece. And this is where a cache can actually bite you. First, a mindset thing. A cache is allowed to lose your data. It is just a rebuildable copy. So a miss is normal, never an error. And there are two different reasons a copy disappears, which people mix up. One is expiration. Its timer ran out. The other is eviction. The cache ran out of space and had to drop something to fit new stuff. So an item with a 1 hour timer can get evicted after 1 minute if the cache fills up, which means your code must always handle it. It is not in the cache even before the timer. A miss is normal. Now, the big one. Caching protects your database right up until the one moment it does not. Picture a really popular key, let's say your homepage, getting 5000 requests a second. all served from that one cached copy. Now, that copy's timer expires, and rebuilding it, doing the real slow work, takes let's say half a second. So, in that half a second gap, every single request that arrives also misses, and each one goes off to rebuild the same thing. That is 5000 a second. For half a second, about 2500 requests, all hammering the database at the exact same moment just to rebuild one value. That is called a cache stampede or a thundering herd. And it can knock over a backend that was sized assuming the cache would soak up the load. So, a cache expiry can actually be more dangerous than the steady state you planned for. So, how do we fix it? The main trick is honestly quite simple. It is called request coalescing. When that hotkey misses, you let one request go and rebuild it, and you make everyone else just wait for that one result. So, 2500 rebuilds collapse into one, and the database barely notices. One request does the work, everybody shares the answer, and this is a well known standard trick. Nginx has it built in, and CDNs call it request collapsing. There are two more tricks worth knowing by the name as well. You can serve the stale copy for a moment while one fresh refresh runs in the background, and you can jitter the timers so 1000 keys do not all expire at the exact same instant. But coalescing is the main one. One rebuilds, everyone waits. Okay, let's pull it together. Everything we did lives in a little triangle: hit, miss, stale. A hit means you have a good copy, fast and cheap. But remember, only hits are fast, so a cache is really a bet on your hit rate. A miss means you do not. You pay full price, and that is normal, right? Until everyone misses at the same moment and you get a stampede. And stale is the whole hard half. Your copy might be wrong because the database has the truth and the cache only has a copy. And that one line, honestly, is the entire video. The database has the truth, every cache is just a copy. You have to decide when to trust. And that decision, how long to trust a copy, there is no universal number to it. It is a product choice. How bad is a stale value really? And the nice thing to realize is that a single page is not one freshness. Your CSS and images can cache for a year. The description, a few minutes. The price, maybe 60 seconds. And your cart, your logged in stuff, that is personal. So it never goes in a shared cache at all. Same page, completely different rules per piece. And one last trap. It is on the screen here and it trips up basically everyone. There is a HTTP setting called no cache. And despite the name, it does not mean do not cache. It means store it, but recheck first. The one that actually means never store a copy is no store. That is the one for your bank page. Mixing those two up is the most common caching mistake there is. So that is caching end to end. And look at the whole path now. You ask for something and it checks your browser cache, then the CDN near you, then the app cache in front of the database. At every single stop, the same two questions: do I have it? And can I trust it? And if the answer is yes, you never even reach the database at all. Everything in front of the database is just a copy, quietly moving the answer closer to you, as long as you know when to stop trusting it. Next up, we will look at rate limiting, how a service protects itself when too much traffic shows up at once. But for today, that is the whole thing. See you in the next one.